Okay, let's just jump right into this explainer and tackle the massive elephant in the room that pretty much every product and engineering team is sweating over right now, and that is skyrocketing inference costs. We're living in this moment where the default reaction to a struggling AI agent is just, throw a bigger, more expensive model at the problem. But today, we're going to dig into some seriously compelling new data that completely challenges that instinct.
Right, so this is the ultimate executive dilemma for product leaders today. It's fueled by this pervasive myth that simply buying a bigger, denser model is literally the only way to scale your system's capability. We naturally assume that if an agent fails, well, the model just isn't smart enough. But what if the problem isn't the engine? What if the problem is that you haven't actually built a car around it?
The paradigm shift here is simple, but it fundamentally redefines how we approach AI development. An agent isn't just a model. In reality, a functioning agent is a reasoning engine that is completely surrounded by a customized harness. It is the combination of the two that actually gets the work done. And once you realize the model is just one piece of a much larger puzzle, it completely flips the script on where you should be investing your time and your budget.
Section 1. Anatomy of a harness. What exactly surrounds the model?
Let's demystify what this actually looks like under the hood. Because despite all the magical aura surrounding AI right now, the harness is essentially just traditional, highly manageable software engineering. The model is just the core engine sitting right in the center, but the harness, that deterministic code keeping the probabilistic model in check, well, that's the car, the road, and the traffic laws guiding it. In a truly mature system, the model itself might only account for about 10% of the overall architecture. The harness makes up the other 90%. It's this surrounding infrastructure that gives the model state, execution capabilities, and strict enforceable boundaries.
When we break it all down, the harness is basically composed of 6 concrete elements. You've got your instructions and rule files that define the agent's persona. You have the tools and APIs connecting it to the real world. Then you've got sandboxes for safe execution, orchestration logic to route tasks, guardrails to catch bad behaviors before they deploy, and observability to track token costs and latency. These are the specific elements dictating how the model interacts with the world. And here's the best part. Not a single one of them requires you to train a neural network.
So, the absolutely crucial takeaway here is that by focusing on the harness, control, and intellectual property shift entirely back to your internal product team, rather than just sitting with the model provider, you aren't just renting intelligence from a frontier lab anymore, you are building proprietary infrastructure. Your real competitive moat becomes your custom tools, your specific routing logic, and your highly tuned guardrails. And all of that stays entirely in-house.
Section 2. Small models, massive gains. Exploring the strong to weak transfer proof.
To see this in action, we have some startling 2026 data from Salesforce AI Research. They explored what happens when you take a weak target model and wrap it in a highly optimized scaffold. The numbers are an absolute showstopper. A raw GPT 5.4 mini scores a 0.488 baseline on complex tasks. Now, if you pay up for the massive unscaffolded GPT 5.4, you only get to 0.619. But, and this is wild, by building rigorous scaffolds around that cheap, small mini model, its performance jumps to an astonishing 0.912. It literally dwarfed the massive, much more expensive model.
This is just a massive revelation for engineering teams. It means you can effectively substitute expensive raw model capability with smart inference time structure. You're essentially transferring the cognitive load away from the model and directly into your code. If you can define the rules of the task clearly within your harness, you simply don't need to pay for the deepest, most expensive reasoning engine on the market.
Section 3. What actually moves the needle? Let's talk about where to actually spend your engineering effort.
But how do you actually build this thing? It's one thing to know a harness works, and a completely different thing to know which parts of it actually matter. Across 3 separate 2026 studies, the data clearly shows that simply writing a larger volume of scaffold code barely helps at all. That only correlates with accuracy at a really weak 0.22. But shifting reasoning to deterministic rules, a concept called deterministic offloading, is a massive driver of success, boasting a strong correlation of 0.72. So it's not about writing more code, it's about writing code that purposefully takes the guesswork out of the model's hands.
It turns out, the more work you convert into executable structure, the less cognitive load remains for your weak target model. Think about it. If a problem can be solved with a simple schema check, a strict format enforcement, or just a traditional Python script, let the code do it. Save the model's probabilistic thinking only for the ambiguous, high-level reasoning tasks it's actually meant for.
Section 4. The headroom warning. Let's look at when adding more harness actually backfires.
Now, to keep things completely objective, a heavy harness is not a universal magic wand. There is a very real concept in this space called headroom, and you really need to know when backing off is the better choice. In a striking 9 out of 20 matched cases in the Salesforce study, adding more harness to a target model that was already near its performance ceiling actually made benchmark scores worse. When tested against a very strong target model like Gemini 3.5 Flash, almost every single builder accidentally introduced at least one regression.
This happens because as models get stronger, their available headroom for improvement naturally shrinks. A super rigid harness can actively disrupt the model's native logic. If a model already knows how to navigate a complex multi-step problem gracefully, forcing it through a clunky, rigid set of deterministic guardrails is kind of like putting training wheels on a motorcycle. It doesn't help. It just slows the whole thing down and causes crashes.
Section 5. The product leader's choice. How to allocate your Q3 budget.
So, with limited engineering hours and finite budgets, how do product leaders actually make the call between funding a better model or funding a better harness? Well, you run what's called the compilable failure test. You sit down and you sort 30 of your recent agent failures. Ask yourself, how many of these were procedural? Like, did the model hallucinate a completely fake API endpoint because it felt a little too creative? Did it drop context or forget basic JSON syntax? Or, on the flip side, how many were actual deep reasoning breakdowns where it fundamentally just didn't understand the logic of the task?
That split right there directly dictates your playbook. If you find that the vast majority of your failures are procedural, like the model outputting JSON incorrectly or calling the wrong API endpoint, you engineer the harness. You build deterministic offloading to catch all of that. But if the failures require real, fluid reasoning, like interpreting nuance in a complex customer negotiation, well, that is when you finally open the checkbook and buy the bigger model.
I really want to leave you with this final thought to apply to your own systems. Take a hard look at your architecture today. Look at those monthly inference bills and ask yourself, are you writing blank checks for raw intelligence that your internal team could have simply built a structured harness for? Because the future of AI development isn't just about who buys the biggest engine, it's about who engineers the best factory around it.